morning, everyone. Hope you all enjoyed the past 2 weeks of the summer school. And today we'll have Professor Jason Alicea from Caltech to start the first lecture of the series of lectures in this 3rd week. And Jason is a condensed matter theorist who studied topological systems as well as the applications for topological quantum computing. So Jason has made various interesting proposals for topological quantum computing, and as you probably know, Microsoft is starting quantum computing efforts, and their underlying theoretical model is actually based on one of Jason's proposals. So without further ado, let's welcome Jason to start the lecture.
Well, thank you. Thanks, Liang, for that kind introduction and for inviting me to this fantastic school. So I'm really honored to be here. I'm going to tell you about Majorana-based quantum computing, or at least efforts at realizing Majorana-based quantum computing. So there's an outline for what I hope to cover in all 3 of my lectures, certainly not just today. So I'm going to start by giving you a kind of bird's eye view of what this field is all about. I'm going to introduce to you in a somewhat general way non-abelian anyons and topological quantum computation. After that, I'm going to hopefully make these ideas more concrete by describing the physics of some toy models. First, the Kitab chain, and if time, I'll describe a toy model for a 2-dimensional topological superconductor that can also be used for getting these Majorana objects and performing quantum computation with them. Then I'll show you how you can actually realize the physics of those toy models in practical experimental realizations. I'll then show you how you can detect the presence of Majorana modes, then read out the states that they're encoding, and finally characterize qubits made out of Majorana-based hardware. Okay, so I have no idea how far I'll get in that program. It's kind of ambitious, but I far prefer having a lot of feedback and conversation with the audience at the expense of going through, at the expense of scrapping some of that material. Okay, so let me begin by reminding you of one of the very basic ingredients in many particle quantum mechanics, namely the idea of indistinguishable particles and their exchange statistics. So suppose you have some system of identical particles. And imagine that you take a pair of those identical particles and exchange their positions. Exchange statistics describes how the wave function transforms under such an exchange. So there's only a few different kinds of outcomes that nature allows. So 2 you're already familiar with from early on in your physics education. If you were dealing with bosons or fermions, the wave function either remains invariant in the case of bosons or it gets a minus sign in the case of fermions. So it turns out that all elementary particles that exist in our universe are necessarily bosons or fermions. There's actually simple topological reasons for that. But that doesn't quite exhaust the full set of possibilities that nature allows us to find. It's an amazing fact that if you take large collections of bosons and fermions, put them together inside of a material, allow them to interact, one can get exotic topological phases of matter that give birth to new kinds of emergent particles called anyons, which have more interesting exchange statistics compared to those microscopic constituents. Right. So anyons come in 2 rough categories. The simpler variety are so-called abelian anyons. So this is already quite interesting. If you exchange 2 abelian anyons, then your wave function acquires a complex phase factor e to the I alpha, which is intermediate between plus or minus 1. We call these abelian basically because sequential exchanges commute. Order doesn't matter because you're just acquiring a phase factor for each individual exchange. So I'm going to be interested in the more exotic kind of anyons, so-called non-abelian anyons. where something even more dramatic happens. If you exchange two non-abelian anyons, your wave function actually undergoes a non-trivial rotation in Hilbert space. So in this case, exchange is actually described by a matrix, Uij. So here psi I and psi j are some states in Hilbert space. We'll say exactly what kind of states those are shortly. But because there's a matrix here, we know that matrix multiplication is generally non-commutative. So now order does matter when you perform sequential exchanges, and that's why we call these non-abelian anyons. All right, so my entire set of lectures will concentrate on the physics of non-abelian anyons. And how they can be useful for quantum computation. All right, so I'd like to now go through the physics of non-abelian anyons in some more detail. So I'm going to focus on a particular kind of non-abelian enyon called an Ising enyon, although a lot of what I say here will apply much more broadly to any kind of non-abelian enyon. Okay, so for the sake of discussion, let's suppose that you have some exotic phase of matter that supports these Ising non-abelian anyons. I'd like to give you the three basic hallmarks that make those particles special. The first is that as you start introducing these Ising anyons into your system, one actually gets a ground state degeneracy that grows exponentially. Right? So let's imagine that you start off in a configuration where you don't have any Ising anyons in your system, but you have this exotic topological phase of matter that supports them. Let's further imagine that in that starting configuration, you just have a unique ground state, and that there's a finite excitation gap to all excited states. So here's excitations. And this is the unique ground state that we start from. Okay, so now imagine that you apply some perturbations to your system to basically introduce a pair of Ising anyons. So you might imagine, let's say, dragging a pair of Ising anyons out of the vacuum. Okay, so that's the first pair that I pull out. In the presence of those two Ising anyons, my system will now have not one but two degenerate ground states to choose from. If I pull out a second pair of Ising anyons from the vacuum in a similar fashion, I now have four of these guys, and my system will have not two but four ground states to choose from. If I pull out a third pair from the vacuum, I'll have 8 states, and so on. Okay, so in general, we have 2 to the number of anyons divided by 2 degenerate ground states. So that's kind of a weird feature. You don't usually expect this kind of exponentially growing degeneracy. But ground state degeneracy by itself is not so extraordinary. Okay? So for example, Heisenberg ferromagnet, ordinary Heisenberg ferromagnet has infinite ground state degeneracy. So why should I make a big deal out of this set of exponentially growing ground states here? So to sharpen this question, I'd like to contrast the situation that we get here for these Ising anyons to a more trivial situation where you have some insulator that just has a bunch of free spin-a-halves. And by free spin-a-halves, I just mean a set of spin-a-half degrees of freedom, set of spin-a-halves that don't care energetically whether they point up or down. Okay. So if you have a bunch of free spin-a-halves, and you also have exponentially large set of ground states, and every time you add an extra free spin-a-half, you'll get an extra factor of 2 in the ground state degeneracy. So that appears superficially very similar to what we get for these Ising anyons. Okay, so here I'd get a ground state degeneracy consisting of 2 to the n spins ground states. But this ground state degeneracy here is fundamentally different from the kind of ground states that we get up here. Okay. So there's 2 important distinctions. First, these ground states arising from these spin-a-half degrees of freedom are locally distinguishable from each other. So you can imagine coming in with some kind of magnetometer, which just senses the magnetization for each one of those spins individually, and then you can recover which ground state your system is actually realizing in that set. Okay. In the case of the ground state degeneracy that's produced by these Ising anyons, that's fundamentally impossible. Okay, so there's no local measurement that you can do, even as a matter of principle, to diagnose which of those states your system is actually realizing. Yeah.
So when you pull out two anyons, actually does the energy change from the initial ground state? And like it's like, so there's some energy cost, right? I guess.
Well, okay, so I'm imagining that we've applied some kind of perturbations to the system so that the minimum energy configuration actually does have these anyons in it, inside of them. Now the excitation gap can indeed change once you've introduced these non-abelian anyons, but I'm going to assume that the excitation gap is always finite. And I don't really care about exactly the size of this. So this is pretty schematic, but the thing I care about is having a set of ground states that are separated by an energy gap from all excited states. Okay, so these states are locally indistinguishable from each other. Whereas these ground states are not. Okay. So a closely related property is that this degeneracy that I get for these free spin and halves is fragile. Okay. There's no reason that it needs to be there, and I can easily just remove all ground state degeneracy from this free spin and half problem, for example, by just applying a Zeeman field. Right? Zeeman field would just preferentially, let's say, prefer all spin-ups, and you would go from 2 to the n spins, ground state degeneracy, to just having a unique ground state. In the case of these ground states generated by our Ising anyons, that degeneracy is robust. So you can introduce magnetic fields, chemical potential perturbations, all sorts of arbitrary local perturbations, and as long as they're not sufficiently strong to take you out of the phase that supports these Ising anyons, this ground state degeneracy is robust. Okay, so what we learned from this comparison is that these Ising anyons here must somehow capture unusual zero energy degrees of freedom in order to generate this space of locally indistinguishable and robust ground states that are very different from ordinary spin and half degrees of freedom. Okay. Yeah.
Can you comment on this degeneracy with respect to position of these anyons as well, sort of this continuous degeneracy? Is that
Yeah, okay, so I will comment on this when I get to toy models, but maybe it's worth saying this now. So this degeneracy is not actually exact. When I say degenerate, I mean degenerate up to corrections that are exponentially small in the separation between these anyons. So when the anyons are brought close together, actually this degeneracy gets worse and worse. And in other words, splittings get bigger and bigger, and you lose this local indistinguishability property. But as you drag the anyons farther and farther apart, this degeneracy gets more and more perfect, and the states that are in that manifold become more and more locally indistinguishable from each other.
But I mean, there's degeneracy with respect to like rotating, putting two anyons in various, orientationally distinct configurations. So that's not counted in that degeneracy, or?
No, that's right. Yeah, that's right. So when I refer to this degeneracy, I mean I'm considering the anyons to be at fixed positions.
Good.
Yeah, so that's right. Yeah, thanks. Yeah.
Are you saying that creating the anyons and pulling them apart can all be done using local perturbations to the Hamiltonian?
Yes, in principle, that's right. That's so. Actually, it depends on the kind of realization of these things, but you could imagine applying, let's say, little STM tips to drag a pair of anyons away from each other. But what you can't do is you have to think about this in a dynamical way. So what I can't do, I think, is
No, I meant like local terms to the Hamiltonian. Like there's a Hamiltonian that has no anyons in the ground state, but in order to produce another Hamiltonian that energetically prefers anyons in the ground state, can I have them well separated with local perturbations to the original Hamiltonian?
Yeah, I believe so. Yeah.
Excuse me.
Yeah.
So just one thing. So if you, for example, if you start from the vacuum and then you pull out the two anyons, and they cannot fuse back to anything else. So probably there's like n-1 or something.
Yeah, I'm not counting overall. Yeah, indeed, you're right. So there should be technically a -1 here, and I'll discuss that, I think, in the very, very end of my lectures. Okay. All right. So there's must be some kind of unusual zero energy degrees of freedom that are associated with those Ising anyons. So the important thing that we can take away from this comparison and in the case of Ising anyons, those degrees of freedom correspond to Majorana modes. Okay, so that's the first important characteristic of these non-abelian anyons. They give us this very peculiar ground state degeneracy. So the second thing I've already mentioned, non-abelian statistics, but now we can put this into a little bit better context. Okay, so let me once again draw my collection of anyons that I pulled out of the vacuum. Let's suppose that I initialize my system into one of those degenerate ground states, which I'm going to call psi sub I. And suppose that we then perform an adiabatic braid of a pair of these anyons. Okay, so that exchange will non-trivially rotate my system within that ground state manifold. So this is the same equation I wrote over there, but now we can have a little bit deeper understanding here. So these psi I and psi j correspond to ground states. And this uij that appears here is a so-called braid matrix. And the important thing I want to emphasize here is that that braid matrix is rigid. Okay. And when I say rigid, I mean that the matrix that you get here does not depend on detailed properties of how you perform this adiabatic braid. It depends only on the topology of the braid that you've created. Okay, so in other words, suppose that I choose some particular trajectory to exchange those particles, and you choose a different trajectory. So instead of choosing that path, maybe you do something like this. We can compare answers at the end of the day, and we should find that up to exponentially small corrections, our states were rotated in exactly the same way. Okay, so that's what I mean by rigid. All right, so the third property corresponds to non-trivial fusion. So what I mean here is the following. Suppose you take two of these anyons and now do the inverse of what we did up there, so bring a pair of them together. So these two anyons can actually form at least two different kinds of particles. In the case of Ising anyons, it's two different possibilities, but for more general kinds of non-abelian anyons, you can form 3 or more kinds of particles. Okay, so in the case of Ising anyons, there's a relatively simple looking equation which describes this fusion. So there's the equation, sigma cross sigma is I plus psi. So the physical content is actually very simple. The left-hand side tells you that if you take two Ising anyons and bring them together, so these sigmas denote Ising anyons, they can either annihilate each other, which corresponds to this identity, or they can combine into an extra fermion, which is psi. Okay, so to put this in context, you might imagine, let's say, taking an electron and a positron. Those are antiparticles of each other. If you bring them together, there's no question they're going to annihilate. Right? So here, there's not a unique answer. So these two Ising anyons can come together and annihilate each other and return the system back to its original configuration without any anyons at all, or you can get an extra fermion out. Okay. So this probably looks a little bit cryptic, but once I describe my first toy model, we can get better intuition for how this can actually arise. Yeah.
So, what kind of fermion is it? Is it charged, and I guess does it interact with the system, or is it sort of a free particle?
That's not a universal question that I can answer. So it depends on how you're realizing Ising anyons. So for example, if you do this in the fractional quantum Hall context, that fermion might have charge, it might be neutral. In the cases that I'm going to be dealing with superconductors, it's always well, it's a bit funny to talk about charge in a superconductor, but it will be, on average, an electrically neutral fermion. Okay, so that's the three base. Oh, go ahead.
So number 2, it looks like the psi particles are what are braiding. But in number 3, you said that this actually the sigmas that are the anyons.
I just realized, I never noticed this, but this psi and this psi are completely different psis. But thanks for pointing that out. So these guys that I'm braiding are actually sigmas in the language of this fusion rule. Okay.
So that psi is a many-body wave.
This is a many-body wave function, exactly.
Depends on all the coordinates.
Exactly. Yeah. Yeah.
Are 2 and 3 like always come together?
Oh, thanks. I actually forgot to say this. Yeah. So indeed, it's very interesting. So non-abelian statistics implies non-trivial fusion rules, but also the inverse is true. If you have non-trivial fusion rules, you must have non-abelian statistics. And it also turns out that both of these two properties rely critically on the presence of this ground state degeneracy. So in fact, all 3 of these characteristics are intimately tied up with each other. You can't really have one without the other two. Yeah.
Sorry, I'm still just a little confused about the right-hand side of this equation. Then, are you not conserving electrical charge or like fermion parity? Is that somehow sidestepped, or is there some of this that will keep those conservation?
Yeah. Okay. So global fermion parity must always be conserved. So global fermion parity will come in reducing the possible fusion channels that you have access to, depending on how many anyons you have. So for instance, if I just had 2 Ising anyons and I bring them together, I don't actually have access to this psi fusion channel. I only have access to the identity fusion channel, which makes some sense, because if I just had 2, the only possible way in which I could have formed those was pulling them out of the vacuum. And if I just bring them back together, I'm bound to return to the vacuum. So, but it's different if I have, let's say, 2 pairs of Ising anyons. Then I actually have, both of those, both pairs can actually fuse to a fermion, in which case I'm preserving global fermion parity.
But then the second pair has to fuse into a fermion as well.
Yeah, both pairs would have to fuse into a fermion, or both pairs would have to fuse into identity. But you can't have, there's some kind of global conservation laws that would prevent you from having just a single pair of Ising anyons that fuse into psi. Yeah.
Is Bragg matrix unitary?
It's a unitary matrix.
What do you mean by trajectory here?
Oh, by trajectory, I just meant the specific path along which those particles took to undergo an exchange. And so that's not unique. There's an infinite number of possible trajectories that I can take to adiabatically exchange a pair of anyons. And the beauty is that this matrix does not depend on that detail, provided that the paths are all smoothly connected to each other.
So, but when you're doing this exchange, I mean, you're thinking of this as just changing adiabatically parameters in the Hamiltonian or
That's
in
right.
the wave function or something.
Yeah, yeah.
So
Yeah.
is there any kind of dynamical phase there? I mean, when you do adiabatic evolution?
Yeah, so there will in general be a dynamical phase, but the important thing is that dynamical phase does not depend on which state you're actually, which state. In other words, it's independent of I and J. And that I just mod out by that. It's not important. Yeah.
So in the case of 2 anyons you were talking about, so if I brought them together and then they fuse into identity, does it mean that the parameters that I have also
You mean after fusion?
Yeah.
Yeah, so you can indeed imagine something like that. So let's imagine a 3-step process. Let's start in our unique ground state, pull out some anyons, braid them, and then bring the anyons back together. And then indeed, I've returned the system to the initial Hamiltonian that I had at the very beginning. But I don't necessarily return the quantum state of the system back to the original ground state that I started from. If all these anyons fuse into the identity channel, I would. But in general, there's psi fermions that can be generated. And so I might actually end up in an excited state after this initialize braid fuse protocol. That's actually a feature rather than a bug. It's very important that's possible. Yeah.
So in point second, is it a global unitary?
What do you mean by global unitary?
Unitary acting on all possible anyons, not locally on each individual anyon.
Well, this unitary acts on the many-body wave function for the system. So that many-body wave function in some sense knows about all the anyons, although the particular braid matrix that appears here, the form of that would just depend on the particular anyons that you've chosen to exchange. Yeah.
Just one last.
Sure.
So when you write the fusion equation, so there are these nice physical words attached to it, but at a mathematical level, is it correct to say that you're saying on the left-hand side it's a direct product, on the right-hand side you have a direct sum of those two representations?
Yeah, exactly. Yeah.
What does the label I and J?
So I and J, so those label ground states. Yeah.
When you say non-trivial fusion, you mean multiple fusion channels?
Exactly. The non-trivial aspect is at least 2 possibilities on the right-hand side. Actually, if you were to consider a billion anyons always have a unique fusion product. So that's another distinguishing characteristic. Okay, this is wonderful. Actually, I'm very happy to have a lot of this discussion. I may not get very far in my outline, but that's perfectly fine. Okay, so hopefully everyone is at least intrigued. I think this is pretty cool physics in its own right. There's also a technological application of all this. So this is something that Alicea Kitab taught us a number of years ago. He outlined a pathway towards building a so-called topological quantum computer using non-abelian anyons that was intrinsically immune to decoherence at the level of your system's hardware. So let me sketch the basic idea for how this goes. This set of locally indistinguishable robust ground states furnish a space of intrinsically fault-tolerant qubit states. To appreciate why those states are fault-tolerant, it's maybe worth going back to this spin example. Right, so when I have a bunch of free spin and halves, I might have degeneracy, but that's a statement that only makes sense in some time average sense. If you have coupling to the environment, that environment can produce, let's say, random magnetic fields, random Zeeman fields, which would cause some random time-dependent splitting between the spin-up and spin-down states. Okay? And that random splitting of those spin-up and down states causes your qubit to dephase. Right? So in the case of these non-abelian anyons, this degeneracy is robust, and so you can have noise from the environment, but that noise doesn't cause that wiggling of the states, which leads to dephasing, and so you have some intrinsic resilience against noise. It's kind of built in by virtue of the kind of particles that you're using to generate those states. All right, so at that level, we have fault-tolerant quantum memory, a fault-tolerant way of encoding quantum information. We also, by virtue of non-abelian statistics, have a way of generating fault-tolerant quantum gates. So here you can view these braid matrices as representing unitary rotations within on your qubit states. And the point is that those matrices, again, are rigid, and so by braiding these things around each other adiabatically, you impart some very precise unitary rotation onto your qubits. So fusion also is important in the story. We can exploit fusion for readout. So if you want to perform some sequence of braids to process your quantum information, eventually you'd like to read out that quantum information, and to do so you can basically bring your anyons together, and by detecting whether they fused to the identity or gave you an extra fermion, you can infer the state of the qubits when the anyons were all far apart from each other. And so the basic idea is we can, in this fusion step, we intentionally convert those locally indistinguishable robust ground states into locally distinguishable, not robust ground states, which we can then read out using conventional tools. So that's the idea. All right, so it's a beautiful idea. I think it's not controversial to say that, as a matter of principle, this is the best way to build a quantum computer. I don't think that anyone would disagree, as long as I put the words "in principle" there, in all caps. Of course, the question is, how do you actually build the hardware to bring this idea to experimental life? So that's not so easy to do. Getting phases that harbor non-abelian anyons of any type is a serious challenge. There has, however, been some paradigm shifts in the last decade or so that have transformed the way in which we approach the problem, which we try to build these inherently fault-tolerant topological qubits. So I want to describe these paradigm shifts using a bit of fluff that I'm going to call the Fisher plot, after my advisor, Matthew Fisher. So when I was in graduate school, he described problems in theoretical physics to me in terms of this two-dimensional space, which had experimental relevance on one axis and conceptual novelty on the other. So where you want to work in this plot is a matter of taste, as long as you shouldn't work too close to the origin, of course, but outside of that, it's all fair game. So non-abelian anyons were invented in the late 1980s by mathematical physicists like Moore, Seiberg, Witten, and others. And back then, this problem was deep in what one would call la-la land, very far along the conceptual novelty axis, but had no obvious experimental relevance whatsoever. In 1991, there was the first major boost towards experimental relevance. In particular, in 1991, Moore and Reed proposed a realization of, in fact, Ising anyons in the quantum Hall context. And their theory work has stood the test of time, and there's indeed active research efforts nowadays working on those non-abelian quantum Hall states. Actually, precisely the regime that Moore and Reed had envisioned. There was another key breakthrough about 10 years after that. In 2000 and 2001, Reed and Green and Kitab showed that actually the essential non-abelian physics of these exotic quantum Hall phases could actually be found in relatively simple topological superconductors that have so-called Majorana zero modes. Well, it depends on, it's a subjective thing, and I'm going to insist that this remains vertical. It took a while, though, before we figured out how we can actually make those topological superconductors in practical ways. But in the last 10 years or so, people have devised a number of blueprints for making so-called designer topological superconductors that are built from things that we already understand and things that experimentalists can work with very well. So maybe it's worth emphasizing, this step from quantum Hall to superconductivity was a very important distillation process. Basically, one took non-abelian anyon physics from the strong correlation realm to the weak correlation realm. It's a very positive thing because as theorists at least, we have lots of tools for predicting the behavior of weakly correlated systems that we can then bring to bear on this very exotic problem. And then figuring out how to realize those obviously was another key step. So I'm going to be focusing for the rest of these lectures on the superconducting realizations of non-abelian anyon physics. Before I get there, though, I want to say one more bit of fluff. I mentioned that there are paradigm shifts, which is somewhat grandiose language. So there indeed has been a lot of transformative understanding in how we can get non-abelian anyons to start to build, hopefully, hardware for a topological quantum computer and put these ideas of Aliceia's to work. But let me just summarize in a crude way where we are now in that endeavor. So an often quoted, but certainly imperfect metric is to think about the number of qubits that have been integrated into a device. So let's think about that metric as a function of time. I'm going to maybe slightly unfairly start time at 1991 when we had the first possible realization of, or first idea for how you might realize non-abelian anyons. And here's present day. I should make sure to label the 0 on the vertical axis. Maybe here's 150. Okay, so in the quest for topological qubits, this is not an especially interesting curve. So it's obviously 0 back in 1991 and has remained 0 to the present day. Conversely, conventional qubits have seen fantastic progress, very exciting progress over the last several years. You've probably already heard about at this school, and maybe even before, about devices that have more than 50 qubits, which is an amazing achievement. So this is a little embarrassing for me. So you might ask, why am I here? Is this just a clerical error? Some oversight on the point of view of the organizers? I hope it's not a clerical error. I think there is really good reason for you to learn about Majorana-based quantum computing, and I'm going to give you two motivations. The first is just from a basic science point of view. I think this is awesome physics. I think it's probably also not controversial to say that this is the most exotic approach to building a quantum computer. All of this is cutting-edge quantum physics, and even by making the leap from 0 to 1 topological qubits, you will already learn great new discoveries about quantum mechanics and organizing principles of nature. So I think even if this disparity continues for a long time, it's still worth trying to push this endeavor, right, just from a purely basic science point of view. The other motivation is more practical and has the long game in mind. Error correction, I don't think anybody will tell you otherwise, is a kind of daunting thing. Right? So if you want to achieve fault tolerance with conventional qubits, what one typically imagines doing is using many physical qubits, maybe hundreds or thousands, to encode a single logical qubit. So there's a lot of overhead that's associated with that, with achieving fault tolerance with conventional qubits. So the hope of topological quantum computation is to mitigate the need for error correction and reduce the overhead by a substantial amount. So I don't know if we'll be able to do that, but that's, I think, a longer-term motivation for why we should still keep an eye on this problem, even if the conventional qubit approach continues to skyrocket. All right. So that's the end of my big picture overview. Any questions before I move on? By the way, everything I said here was supposed to be cryptic at this point. So if you feel a little bit uncertain, it's by design. You should feel a little bit uncertain. And I hope to make a lot of these ideas crisper as I now go to the next step in my outline and discuss concrete toy models where you see a lot of this physics come out in relatively simple ways. All right. Is there a clock, by the way, so I can keep track of time? Okay. And okay, so I'm half done for today.
You go to 10:30.
10:30. Okay. All right. So I'm now going to discuss the Kitab chain. Can I poll the audience who's solved the Kitab chain before? Wow. Okay. So maybe I should ask the inverse: who has not solved the Kitab chain? Okay. Good. Okay. And among the people who didn't solve the Kitab chain, have you solved the transverse field Ising model? Raise your hand if you have. Okay, so you actually have solved the Kitab chain and just didn't realize that you did so. It's actually the same model, just written in a different basis. Okay, so apologies to the people that are already familiar with Kitab chain physics, but I'll go through it anyway. So I want to now consider a system made out of spinless fermions. On an n-site chain with periodic boundary conditions. So I will soon abandon periodic boundary conditions, but let's start there. Here's my n-site chain, sites 1, 2, 3, 4, up to n. I'm going to allow the spinless fermions to hop between nearest neighbor sites of this chain with some amplitude t. And I'm also going to allow pairing. I'm going to allow fermions on neighboring sites to form Cooper pairs with some amplitude delta. So the Hamiltonian will consist of a sum on all sites x via chemical potential term. I'm going to put a factor of a half in front of the pairing and tunneling terms, not for any particular reason. So there's the hopping term. And there's the pairing term. Okay. I think a generally good piece of advice is that we should always take advantage of whatever symmetries we have in our problem. Since I have a chain with periodic boundary conditions, we actually have translation symmetry. We can translate by one site and the Hamiltonian looks the same. And we can take advantage of that translation symmetry by passing to momentum space, so let's do that. I'll assume that everybody knows how to do this exercise and write the Hamiltonian momentum space, and just write down the answer. So we'll get a sum on momenta in the one-dimensional Brillouin zone, minus mu minus t cosine k, ck dagger ck, plus I delta over 2 sine k, ck c minus k, plus Hermitian conjugate. Okay, so we should notice that the this thing that sits in front of ck c minus k, this is a pairing potential. It involves sine k, and so it's it has odd parity. So if you take k to minus k, this changes sign. Okay, so that's very important. We actually have no choice here because I dealt with spinless fermions. Any pairing actually has to be odd parity. But that's the way it comes out. Okay, so what I'd like to do now is try to understand the phase diagram of that model. In principle, we could diagonalize the Hamiltonian in the usual way and get the energies, but I don't want to do that. I want to try to deduce the physics more intuitively. Okay, so let me draw the kinetic energy, which is just minus t cosine k, as a function of momentum within the 1D Brillouin zone. That's just a cosine. Okay, so now I want to just consider a few different values of chemical potential, and I want us to agree on whether the spectrum of the system away from the ground state is gapped or gapless at different values of the chemical potential. Okay, so suppose, let's start with the chemical potential being down here below the bottom of that band. So yes or no question, is the spectrum of the system gapped or gapless when the chemical potential sits here? Okay. Take a second to think about it. Okay, so can I poll people? Who thinks that the spectrum is gapped? Who thinks it's gapless? Okay, so almost. I don't think there's a third option, actually. Okay, is a question meaning? It makes sense? Consider I want to start from the ground state of the system with chemical potential here, and then just ask whether it costs you a finite energy to create the minimum energy excitation in the system, or whether you can create excitations with arbitrarily low energy. Okay. Why don't we turn off delta? Actually, let's turn off delta for a second. So then we just have, it's not a superconducting problem. Right? Here's my chemical potential. Can I create excitations with arbitrarily low energy costs if my chemical potential is down here?
No.
Okay, good. I hear at least several no's. So I hope we can all converge on that. It's definitely not, you have to pay at least this much energy to put a fermion in there. Okay, and that fact actually doesn't change when you turn on delta. In fact, you can turn on delta arbitrarily large, and the spectrum is still going to be gapped. If you're worried about this, just solve the Hamiltonian and diagonalize the spectrum. Okay, so the spectrum is gapped here. I'd like us to all also agree that the gapped phase that we capture here is trivial in every sense of the word. If I take mu to minus infinity, then the ground state is just the vacuum, no fermions whatsoever. Okay, and that's as trivial as it gets. So hopefully there are no objections. I'm going to call this a trivially gapped superconducting state. Okay, so that's good. So what if my chemical potential is up here, above the top of the conduction band? Is the system gapped?
Yes.
It's gapped for the same reason. Is it trivial?
Yes.
It's trivial. It's just the physics of a filled band, right? So this is also trivial and gapped. Okay, so let's consider a more nuanced situation. Suppose that mu sits here, so that we're slicing that band. So we now have a partially occupied band that we're pairing up. Same yes or no question: is the spectrum gapped? Delta is non-zero. Let's turn on delta. Certainly, it's gapless if delta is 0. Right? I have a metal. So now let's turn on delta and ask whether delta successfully gaps out the system. Take a second to think about it, and I'll poll everybody. There's only 2 options now, so everyone needs to raise their hand. Okay, so let me start. Who thinks spectrum is gapped? Okay, and gapless? Okay, I think there's still a substantial abstention, but that's right. You guys were right. So the spectrum is indeed gapped. And we can deduce that the spectrum is gapped by just observing that the pairing potential, which is that delta sign k, is not equal to 0 at the Fermi points. Right? And that's all you really care about, that and the fact that k and minus k are resonant. Right? But as long as that's true, you're guaranteed to gap out the spectrum. Okay, so now we need to decide whether the gapped phase here is the same phase as what we get here and here. Okay. Now, one way of diagnosing that question is to ask whether we can smoothly deform this gap state into, let's say, this trivial gap state without closing the gap at some point. Okay. So maybe let's think about whether we can do that. You might imagine, let's say, starting from this gap state and then dropping the chemical potential smoothly until you get down here, and ask whether at some point the gap necessarily has to close. Okay, so anyone have this is a subtler question, so I won't ask everybody, but does anyone have a idea about, yeah?
But at some point sin k becomes 0, so the pairing potential is 0, but you still have Fermi point, so it's gapped out at some point.
Perfect, exactly. And that happens exactly when the chemical potential hits the bottom of the band, right? So indeed, we cannot actually smoothly deform this state into this state without closing the gap. When the chemical potential gets here, delta sign k is 0 at the Fermi energy, and so there's no gap formation. Okay. So this represents a critical value of mu, and by the same token, if you were to put mu right at the top edge of that band, that would also be gapless for the same reason. Okay. Because sine of pi is also 0. Okay, so this strongly suggests that this phase and this phase are distinct. Okay, and indeed they are. Now there's only, as far as I know, there's 2 ways in which phases can be distinct. One is if they have different symmetries, and the other is if they're topologically distinct. This is a free fermion Hamiltonian. There's no hope of getting anything like spontaneous symmetry breaking, which might lead to a symmetry distinction between these 2 phases. So that just leaves topological distinction. And in fact, these 2 phases are topologically distinct. As long as you have your chemical potential intersecting this band and not at the extreme ends, your system actually realizes a topologically non-trivial gapped superconductor. Okay, so let's write down a phase diagram. As a function of mu over t. Okay, so -1 and 1, those correspond to these critical values of the chemical potential. out here we have trivial superconductors, which flank a topological superconductor. And these points here and here correspond to topological phase transitions that separate those two distinct gap states. Yeah.
You said there's no symmetry breaking, but isn't there
Well, the superconductivity is put in by hand. So for any value of mu, whether you're intersecting the band or not, you always have pairing. So the symmetry of this Hamiltonian is exactly the same, and the symmetry of the ground states are also exactly the same. That would be different if I was, let's say, thinking about spontaneously generating superconductivity from some intrinsic interactions within the system, but I'm not doing that. It's put in by hand. Yes.
Is the topological topological?
Okay, so I think you're asking whether there's topological order here. And is that what you're asking? So I wouldn't call this topologically ordered. I also wouldn't call this a symmetry-protected topological phase, although you sometimes hear that nomenclature. I don't really know what box to put this in. I think one would just say this is a short-range entangled topological phase. But I think some of those words I said are controversial. And
could you also include delta in the phase type?
I could, but it doesn't do anything, actually. So as long as delta is non-zero, that's the exact phase diagram.
I'm just curious what happens as you tune delta to 0.
Well, as you tune delta to 0, this becomes a metal. Yeah, so you still have phase boundaries here and here if delta is 0, but this thing is just a metal. It's a gapless, right? Because you just have a partially filled band. Okay, so to move forward, what I want to do is uncover universal properties of these phases, and if time permits, also the phase transitions that separate them. In order to do so, it's very convenient actually to cherry pick parameters a little bit. So here on out, I'm going to take delta equal to t. And there's no physical motivation for this whatsoever. In fact, it's a pretty unreasonable parameter regime, I would say, to focus on. So the tunneling energy is typically vastly larger than pairing energy scale. I'm just going to ignore that, and just for theoretical expedience, I'm going to set delta equal to t. Just my choice. You can't really argue with it. Okay, so if I cherry pick and I set delta equal to t, then I can rewrite this Hamiltonian in a different way. That will be very useful for things that are soon to come. So let me write the Hamiltonian as follows. Chemical potential looks unmodified. When I set delta equal to t, I just have a single overall energy scale, which I'll pull out front. And what's left inside of that parentheses can actually be factored. So I can write everything else as Cx dagger plus Cx times Cx plus 1 minus Cx plus 1 dagger. So let's make sure that I haven't done anything wrong here. So if we look at, let's say, this term, that's Cx dagger Cx plus 1. That's just this guy here. If I look at that piece, that's Cx times minus Cx plus 1 dagger. So you can get rid of that minus sign by anti-commuting the fermions. So that piece will be Cx plus 1 dagger Cx. And that's just the Hermitian conjugate of that hopping term. So these are the hops. if I look at CX plus 1, that's just the pairing term that's displayed there. And if I look at CX dagger minus CX plus 1 dagger, that's similarly the Hermitian conjugate of that pairing term. Okay, so it's the same model, just written in a way that will be convenient. All right, so what I'd like to do now is understand the gapped phases that appear in this phase diagram. And I want to really understand, more directly what's special about this topological superconductor and how is it different from the trivial superconductor. All right, so topological phases, often a lot of the action happens at the boundaries, so I'm going to now abandon periodic boundary conditions in favor of open boundary conditions. And I'm also going to introduce a Majorana representation of the Hamiltonian. So more specifically, I'm going to decompose my original spinless fermion operators Cx in terms of a pair of so-called Majorana operators. So I'll write 1/2 times gamma b at site x plus I times gamma a at site x. These are so-called Majorana operators. They satisfy the following basic properties. They are Hermitian, so gamma for any subscript alpha is equal to its own Hermitian conjugate. Gamma is gamma dagger. If you square any of those guys, you just get the identity. And if you anti-commute any two different Majorana operators, you get 0. So by virtue of that anti-commutator, these are fermionic-like operators. They have fermionic anti-commutation relations. But it's important to stress that there's no way of assigning an occupation number to an individual Majorana operator. Right? So for these C's, we can, there's a sensible occupation number, which is C dagger C. It's the usual thing that we write down. There's no similar notion, so you might be inclined to write something like gamma dagger gamma and call that an occupation number. But because of these properties, gamma dagger gamma is the same thing as gamma squared because of that, and gamma squared is 1. Right, so individual Majorana operators have no sense of having an occupation. Only pairs of Majorana operators have a well-defined occupation number. Because pairs can be superimposed to give you an ordinary fermion that we know can be either empty or occupied. Okay. Another thing I should say here is that these properties satisfied by these Majorana operators imply that the right-hand side here is consistent with the usual fermionic anti-commutation relations that we associate with conventional fermions. So for instance, Cx squared by Pauli exclusion principle is 0, and if you square the right-hand side, you will indeed find that it's also 0 because of these properties here. And similarly, if you anti-commute, let's say Cx and Cx dagger, that's 1, again by virtue of those Majorana properties. Okay, so this is just, it's a completely cosmetic rewriting of fermion operators. I can always do this. I can, any fermion operator that you give me can always be decomposed in a similar fashion. It may be useful to think about this as kind of like taking a complex number and decomposing it into the real and imaginary parts. Not exactly the same thing here, but it's quite close in spirit. All right, so the important thing I should make sure everybody is comfortable with is that merely writing fermions in this Majorana representation does not in any way guarantee that the excitations of the system have Majorana-like character. Right? In fact, in general, they don't, except in special cases. Okay, so that's the way I'd like to. You have a question?
What does the subscript lambda refer to, and where do I see it on the right side of this?
There's no lambda. Oh, sorry. Yeah, so that's X. That's just the site, and that's the site, and I have two flavors of Majorana operators at each site. There's no choice about that. I have to have, in order to be faithful to my original fermionic Hilbert space, I need to have two Majorana operators per site. Okay, so if you're not familiar with this, it might seem a little bit awkward, but it's just a completely legitimate way of rewriting any fermionic problem. Okay, so I'd like to now take this Hamiltonian that I wrote here and rewrite it in terms of these Majorana operators. Can you say that again?
Are these gamma operators always distinct for A and B? Like for the same X, gamma AX, gamma BX?
Yeah, they're different operators. They kind of have to be because they anti-commute with each other. And so gamma B on a given site anti-commutes with gamma A on the same site. All right, so let's, actually the only non-trivial part is rewriting CX dagger CX, so let's do that. All right, so I have 2 powers of a half, which give me a 1/4. Because these Majorana operators are self-Hermitian, when I put a dagger, all I do is change I to minus I. So that's C dagger, that's C. Okay, so I have a gamma B squared, which just gives me 1. Then I have a minus I gamma A times plus I gamma A. That's also 1. And then from the cross terms, I have an I gamma BX gamma AX. And then from this cross term, I get minus I gamma AX gamma BX. But these two terms are actually the same because these guys anti-commute. So if I reverse the order, I get rid of the minus sign, and then I just pick up an extra factor of 2 there. So this is just 1/2 times 1 plus I gamma BX gamma AX. All right, so the other piece is actually a little bit more straightforward. So CX dagger plus CX times CX plus 1 minus CX plus 1 dagger. So CX dagger plus CX just picks out basically the quote-unquote real part of C, which is gamma B. CX plus 1 minus CX plus 1 dagger picks out the imaginary part, which is I times gamma A. So that looks similar to what we got from the chemical potential term, but the important thing is that these gammas are on different sites, whereas those gammas are on the same site. Okay, so that's all we need. We can now rewrite the Hamiltonian in this Majorana representation. I'll ignore that overall constant of a half in the C dagger C term. Let's see. So there's a factor of 1/2 here, and there's another factor of 1/2 here. So I'll just pull out all those factors out front. And there's also a factor of I common to all the remaining terms. I'll pull that out front as well. And then there's also a minus sign common everywhere. So let's pull out an overall factor of minus I over 2. Then I have mu times gamma bx gamma ax plus t times gamma b x gamma a x plus 1. All right, so there's a nice pictorial representation that we can now appeal to for this Hamiltonian. Let's indicate our original C fermions by boxes. So these will be our CX fermions. So I have a whole chain of these. So this is site 1, site 2, n minus 1, n. And we decomposed each of those fermions in terms of a pair of Majorana operators. So let me indicate those with open and closed circles. So this will, let's see, be gamma A1, gamma B1, gamma A2, gamma B2, and so on down the line. Okay, so mu couples gamma B and gamma A on the same site. So let me illustrate that coupling with dashed lines that just connect these circles within each box. And T couples gamma B at site X with gamma A at the next site over. So I'll indicate that with solid lines. Okay, so if you think about this problem in the Majorana representation, we basically have a chain of these Majorana operators with mu and T just favoring different ways of dimerizing those operators. Okay, so mu wants to dimerize those guys in this fashion within each box, and T wants to have a shifted dimerization where this guy pairs up with this one pairs up with this one, and so on down the line. All right, so I want to just look at special snapshots of the two GATT phases that we identified, the trivial phase and the topological phase. And I'm going to cherry pick things so that the physics just immediately jumps out at us. Okay. Let me draw out this phase diagram one more time. I'm going to indicate minus infinity here. So here's the trivial superconductor, trivial and topological. All right, so I'd like to examine two special limits. The first one corresponds to taking mu over t equals minus infinity. Let's call that case 1. And the second case will correspond to taking mu over t equals 0. So that parks us deep into this topological phase. All right, so in case 1, I can take mu less than 0 and t equals 0. So that pins us over here, right? We're in the trivial phase. Okay, so in this corner of the trivial phase, I only have this coupling between Majoranas within the same box. I just have this mu term and nothing else. So in this case, there's actually there's not even any coupling between adjacent sites. This coupling will cause these two fermions to just form in some ordinary this coupling causes those two Majorana operators to form an ordinary fermion that costs finite energy to occupy. Same thing all the way down the chain. And so we have a unique ground state in this case, which is just a trivial product state without any entanglement between sites. So it's actually a little awkward, I would say, to describe this limit in Majorana language. It's actually much more intuitive to go back to the original CX fermions. Right? So if t is 0, then I don't have that second piece. I just have this chemical potential. And if mu is less than 0, then in the ground state, you just want no fermions whatsoever. And if you want to add a CX fermion, you have to pay energy mu. Okay, so we have a trivial unique ground state with no entanglement between sites. Okay, so let's look at case 2. So now I want to park myself right in the center of that topological phase. So we can take mu equals 0 and t greater than 0 in this case. All right, so now I only have t. So that's the pattern of couplings that I now have. So similar to what happened over here, this Majorana operator and this Majorana operator will be combined into a single fermion that costs you finite energy to occupy. Same thing down the chain. So the bulk of the chain becomes completely gapped, which is compatible with what we observed for the chain with periodic boundary conditions. But we see that something special has happened at the endpoints. Okay, so there are unpaired Majorana operators, one at each end. I'm going to call these gamma 1 and gamma 2. And those correspond to 0 modes, which will encode an unusual kind of degeneracy, as we'll see. All right, so at this point, I would like to make a number of comments. Let's see. Is there another board behind this one? Okay. All right. Okay. So. Oh, there's. Oh, okay. Perfect. Gotcha. All right. So let's write an explicit expression for gamma 1 and gamma 2, or end unpaired Majoranas. in terms of our original CX fermions. So gamma 1 is basically just the imaginary part of C1. So it's C1 minus C1 dagger divided by I, whereas gamma 2 is the real part of Cn, Cn plus Cn dagger. So I'm basically just inverting the relationship up there. Right? So gamma 1 and gamma 2, they don't appear in the Hamiltonian. And in fact, they commute exactly with the Hamiltonian. And since they commute with the Hamiltonian, you can act with gamma 1 and or gamma 2, and you're guaranteed to not change the system's energy. In other words, they're zero modes, right, by definition. From gamma 1 and gamma 2, I can introduce a new but non-local fermion. I'm going to call that non-local fermion D, and it's going to rise from just a superposition gamma 1 plus I gamma 2 over 2. So notice that that looks very similar to the Majorana decomposition I had from my original CX fermions. I'm just combining our two zero modes to get some kind of new complex fermion that has a well-defined occupation number. Okay. So again, gamma 1 and gamma 2 have no sense of being occupied or not, but this fermion does have a well-defined occupation number. Okay, so since gamma 1 and gamma 2 commute with the Hamiltonian, I can add or remove a fermion from that D level without changing the system's energy. Right? And therefore, we have a ground state degeneracy. All right, so we have a twofold ground state degeneracy, and this twofold ground state degeneracy is a special thing. It's a topological ground state degeneracy, and we can just label those two ground states by the occupation number of that D fermion. Okay, so if 0 is a state where that D fermion is absent, then I can construct another state, D dagger acting on 0, which I'll call 1, in which that fermionic level is full. So those two ground states, 0 and 1, they carry opposite fermion parity. So in other words, if there's a total even number of my original spinless fermions in state 0, then there would be a total odd number of fermions in this state 1. So we should pause to reflect on that. This is a very peculiar situation to find in superconductors. Typically in a superconductor, your ground state would like to have an even number of electrons so that every single electron can find a partner to pair up with. And usually if you want to have an odd number of electrons, you have to pay some energy cost for having an unpaired electron. So in this situation, that energetic distinction between even and odd parity states ceases to exist, and that's the physics of these Majorana zero modes. Yeah?
This is sort of only because we're not considering any perturbations to the Hamiltonian that would correspond to connecting the two ends back together, because if you had periodic boundary conditions, you're basically just picking one site and saying this is my Majorana zero mode, and only in the sense that you physically cut and separate those two.
So I'm glad you brought this up. So how do we reconcile this picture with ground state degeneracy with the picture from periodic boundary conditions, where we definitely get a unique ground state? So the idea is that if I have periodic boundary conditions, then I have an additional term in my Hamiltonian, which looks awfully awkward in this picture, but that connects gamma 2 with gamma 1, and so there's no distinction between the. There's absolutely nothing special about gamma 1 and gamma 2 if I have periodic boundary conditions. But the neat thing about this topological superconductor is that wherever you decide to cut that chain to introduce ends, you'll always have unpaired Majoranas. So somehow the presence of these Majorana zero modes at the ends of the chain is kind of encoded in the bulk Hamiltonian in a system with periodic boundary conditions. Okay, so I've cherry-picked things. Oh, go ahead. That's exactly what I was about to comment on, so thanks for a perfectly timed question. So I cherry-picked things, right? So you should be wondering, what happens if I move away from t equals delta and u equals 0. If you do that, then what happens is that our zero modes are not perfectly localized to one site, as they were in my cherry-picked Hamiltonian. Instead, the wave functions associated with those Majorana operators will bleed exponentially into the bulk over some characteristic length scale xc, which is the coherence length for that topological superconductor. So this is gamma 1. This is gamma 2. So because those operators are not perfectly localized, this degeneracy will not be exact. So our 0 and 1 states will be split by some amount which goes like e to the minus L over xc, where L is the separation between those zero modes. But the idea is that we can make this arbitrarily small by just pulling those Majorana operators, by making the system bigger and bigger, or equivalently shrinking C. Yeah?
How is this coherence length related to the Hamiltonian parameters?
So in this case, it would be basically the Fermi velocity divided by the excitation gap in the system. And those, both of those parameters vary depending on exactly where chemical potential is and how big delta is.
That commutativity of gamma 1, 2 with H, that's all set to equal 0. Right?
Yeah, exactly. So if we chose different parameters, but still inside of the topological phase, that's important, then this would not be 0 on the right-hand side, but it would be something that's similarly exponentially small in L over xc. So for the most part, almost everything I say and have said in so far in this lecture should be understood as modulo such exponentially small corrections. Right? So these degeneracies are never exact. There's always some small splitting. Those states will never be perfectly locally indistinguishable. They're perfectly locally indistinguishable modulo these kind of exponentially small corrections. For the most part, until the very end, I'm not going to explicitly say up to exponentially small corrections, but you should be aware that there's that footnote that should be appended. Okay, so I'm technically out of time. What's the protocol? Should I just quit here, or?
Just ask a question. Break for coffee.
I'm at a slightly unnatural stopping point. That's the only reason I ask. But
Well, how much time do you need?
I don't know. Maybe I'll just quit here, actually, and I don't want to eat up too much of the coffee break. So, okay. So, any questions before we? Yeah. You mean this guy or this here? I'm not sure if I can. So this is a detailed thing. If you want to, let's see. I mean, you could imagine, let's say, considering a semi-infinite chain, but have parameters arbitrary. I mean, have parameters not fine-tuned as I've done so here, and then if the chain is semi-infinite, then you can solve for an exact zero energy mode that commutes with the Hamiltonian, and you'll see that if you, let's say, try to write that zero mode operator as just, let's say, the leftmost Majorana, you try to commute with the Hamiltonian, you're going to end up with some other operator that sits nearby. So you need to add something else to that zero mode operator to cancel off this piece. And when you add that new thing, you commute with the Hamiltonian, you'll generate something that's a little bit farther over in the chain. And so you have to just do a non-trivial calculation, I think, to find the wave function. But this is what you'll get. I'm not sure I have a more intuitive explanation beyond that. I mean, you can also use a kind of what else could it be argument. I don't know how satisfying that is, but there's a gap here. So the zero mode, can't completely delocalize because there's a gap, and the most it can do is kind of evanescently decay into the bulk with a length scale that's determined by the gap. But okay, so once you accept the fact that these things are not perfectly localized but have some exponential tails, then gamma 1 and gamma 2 will have some degree of overlap, okay, unless you fine-tune things. And that degree of overlap will cause those two fermions, gamma 1 and gamma 2, to have some non-zero energy splitting, and that's exactly what this is. Okay. And since the overlap is exponentially small in their separation, so is the splitting. Okay, any more questions? Okay, well, I guess I will see you guys later.